Okay, so today we are going to jump into our next unit, which is Introduction to Calculus. Our first topic here is this idea of limits, and limits is a huge foundational topic in calculus. Today we're going to look at how to evaluate limits graphically. First thing to understand is that limits talk about the behavior of a graph. So when we are looking at limits graphically, we are actually asking ourselves, as the graph of a function approaches an x value, what y value is the function approaching? So notationally, that looks like this, where this piece right here is read as the limit as x approaches c of our function equals L. Okay, so you can see that I have that spelled out below how we read that, right? We say the limit as x approaches c of f of x, and in this case, we can identify it to be L. It's important to understand that depending upon our situation and setup, that c and L are going to be changing, and you'll see that in the examples below. But in order to make this claim, this idea of a general limit here, to say that the limit as x approaches c of our function equals L, we actually have to look at that limit from both the left and the right hand side. So in this second box, you see a slightly different notation. You can see that it says there's a negative symbol up above the c, and we read this as the limit as x approaches c from the left of f of x equals L. Okay, so in your limit notation, if you see a small negative sign above the c value, you know that you're looking towards that x value from the left-hand side. Okay, and again here, we're told that the limit as x approaches c from the left is actually L again, so we can fill in that blank. Naturally, we should then also look at the limit as x approaches c from the right, and hopefully it's not surprising that you're seeing this idea, seeing this symbol of a plus sign to denote that we're coming from the left. So we read this statement as the limit as x approaches c from the right of f of x is L. So again, we fill out L here. Definitely be patient with this idea while we work through some examples. It's kind of hard to wrap your head around initially, but hopefully once we work through example 1, things will make a bit more sense. So example 1, I just want to take you through where all of this came from. Okay, so where all these limits and evaluations of the functions came from. We're going to use this graph h of x that's shown here, has this semicircle with a couple linear components. We see a removable discontinuity. See, there's a hole here, but it's actually defined elsewhere. And then we have a hole right here. And those are going to play some different roles as we look at limits of this function and as we do some evaluating of this function. So part A, I want to look up first. It says, right, if I were to think of what this says, I'm asking myself, as x approaches three, h of x, my graph, is approaching 2. Notice it doesn't say that as x approaches 3, h of x has a value of 2. I don't care about the value here of h of x here. I'm interested in the behavior of the graph. So looking at my graph, I need to decide, as x approaches 3, what is our function doing? Okay, so we have our value right here of 3, and we need to look at that from both the left-hand side and the right-hand side. And we'll do that by tracing the behavior of our graph as we approach that value of 3. So from the left-hand side, we can approach 3, and from the right-hand side, we approach 3. And we can see that it's obtaining a value, if I read over, a value of 2. Okay, so that tells me that as x approaches 3 of h of x, the limit is 2. Okay. In this next one, B says, what's happening as x approaches 0 of h of x? Well, apparently we're making the claim that it's 2, but it would be helpful to understand this. So we want to be approaching x equals 0, so we're looking from the left and from the right, but we need to look at the behavior of our graph. So we're going to look from the left to the right as x approaches 0, and then from the right to the left as x approaches 0. Now, it's really important to understand that we're approaching the value of 2. We're approaching the value of 2. So we get to say that the limit as x approaches 0 of h of x is 2. I'm not asking you for what h of 0 is. That's something different, and we'll get to that a little bit later. So we'll ignore that thought for right now. Part C, we're looking at the limit as x approaches 4 of h of x. So we know that we're going to approach this x value from the left and from the right on our function. So from the left, we see that our y values are trending down towards 0. And from the right, as we're getting closer to 4, our y values are trending down to 0 as well. So we can make the claim over here that the limit as x approaches 4 of h of x is 0. Okay. Part D is asking what is the limit as x approaches 6 of h of x, and the claim is that it's 3. So let's see if we can figure out why. So again, we want to look at what our function is doing as x is getting closer to 6. So x is 6 is right here. We want to see what's our function doing from the left and from the right. So we need to go ahead and trace that behavior. From the left, as we approach x equals 6, we see that our function is approaching this value up here of 3. And we see that that is mirrored on the other side as we approach from the right-hand side. We are also getting that value of 3. Much like in B, we are not asked for the actual value. We're asked for what are we approaching on either side. Okay, so we can go ahead and make the claim that the limit, excuse me, the limit as x approaches 6 of h of x is 3. All right. Here, this is kind of, I've been hinting at this, parts E and D. These are very different. This asks you, what is the value of h of x at x equals 0? So we're going to go look at x equals 0 and read up to our function and see that there's a hole. Okay, that hole that we're seeing in our function is represented here by the D and E, that does not exist. That means that our function does not have a value, an output value at the input of 0. Similarly, in F, if you go to x equals 6, we want to know what is h of x. So x equals 6, we actually read up and we see an output value of 1. Okay, notice that it's not up here at 3. There's a removable discontinuity. The point of definition is actually at y equals 1. Okay, big point here is that f, this value of the function at 6, and D, the limit of the function as x approaches 6, those are very different. And the same thing here with h of 0 not existing. That's very different than the limit as x approaches 0, where we saw that that was 2.